Previously to this class period, when we've talked about continuity, and this is more of like when we went back to the 12 basic parent functions, like at the beginning of the school year, we talked about continuity with what was called the elementary definition, meaning we could draw the entire function without picking up our pencil. Do y'all remember talking about continuous versus not continuous functions? If we could draw the whole thing without picking up our pencil, it's continuous. But in calculus, we're going to define that a little bit more. The definition of continuity is this right here. So we're going to read this. Has 3 requirements. Oh, I keep missing. I don't want to cover it up. The function f is continuous at some point c, so an x value of c, if, number 1, f of c is defined. Number 2, if the limit as x approaches c exists. Number 3, if the limit as x approaches c is the same as the evaluation at c. What that means for you and how we can translate this into usable math terminology is for that first requirement, what we are going to do is we are going to plug in the value c into the function and make sure it is not a whole and it's not undefined. Probably not. Number 2, we want to check to see if the limit exists. So for the limit to exist, that means we need to check the left side and the right side of the limit to make sure they're the same point. Then we take the answer from number 1 and the answer from number 2, and we verify that they're the same number. Okay? If any one of the 3 requirements is not met, then the function is not continuous. And so what we're going to be doing today is justifying whether things are continuous or not with a proof, but with some like answers that look like not an essay, but it's not like a 1, box your answer, you're done. So let's talk about these different requirements, just so you can understand what each one means. In this first box, let me back up. All 3 of these graphs are not continuous at point 2, at c equal to 2. And we'll talk about why for each one of them. In the first graph, is there I am all over the place. What is happening at 2 in this function? What is this? It's a hole in the graph. When there is a hole in the graph at the point you are looking at 2, that's a problem because that means that the function f of c is not defined. The first requirement would be broken. F of c is not defined. Okay, let's look at the second graph. For this one, f of c is defined because there is a colored in dot at the number 2. So f of 2 exists. But if we look at the limits, what is the limit as x approaches 2 from the left side? What's it getting closer and closer to? 5. And if we come down to the other side and we look at the limit as x approaches 2 from the positive side, what is that limit? 3. Are those the same thing? No. So as we got closer to 3 on both sides, even though it exists, the limit itself does not exist. So requirement number 2 is broken for this graph. It's defined, but its limit does not exist. Again, we know it's defined because there's a closed-in dot. So that's what we're looking for at the point 2, for there to be a closed-in dot. Okay, so let's look at the third one. Is there a closed-in dot at 2? Yeah, okay, so it's defined. What's the limit as we approach 2? The limit as x approaches 2 for this function, aren't they both going towards the same number? Yeah, so what's the limit? 2. But here's the problem. if you actually look at what happens when you plug in exactly 2, what's the value of that point? 4. Are those the same numbers? So requirement number 3 fails here. The requirement that the limit as x approaches c for this function, it is not equal to the actual function being evaluated at 2. So that's a problem. If any one of these 3 things happen with the function that you're trying to determine if it's continuous or not at a certain point, then you would say it is not continuous. If you can get through all 3 requirements and they're all true, you can then conclude that it is continuous. Does the 3 things make sense? So the first requirement, remember, is that the function actually exists, that there is a closed dot or a line at the particular point 2, or whatever we're looking at. The second one is that the limit exists, which this one does not exist. And the third one is that the evaluation and the limit is the same number. Cool? So here's how you would answer these kinds of questions. We're going to determine if this function is continuous at x equal to 0 and justify the 3 requirements for each function below. What that means, when we look at question number 1, we need to start with requirement number 1. The first requirement is that f of 0 exists. So in this piecewise function, if I wanted to plug in 0, would I plug it into the top equation or to the bottom equation? Top, why the top? Because it's equal to 0 at that point. So I'm just going to plug it in. And I'm going to make sure that I don't get undefined or I don't get an indeterminate form. And if I do, it already fails. It's not continuous. But when I plug this in, I get 1 minus 2 times the sine of 0. Ooh, do we have our formula charts out? What's the sine of 0? So the angle is 0. Sine of 0 is the angle I'm plugging in is 0. 0. So what's 2 times 0?
0.
And 1 minus 0 is 1, which is a number. It is defined. It is not an undefined term. It is not an, oh my gosh, what is that called? Indeterminate form. So it's okay. We got a number. So we conclude in the first one, therefore, that f of 0 equals to 1 and is defined. Check. We needed it to be defined. We needed it to exist for us to bypass the first requirement. Then we go to the second requirement. The second requirement is that the limit exists. So we have to check both sides of the limit to see if it exists. With a piecewise function, if we wanted to find the limit as x approaches 0 from the left side, you're just looking for where things are less than. So we're going to be using the top formula as the left side and the bottom formula as the right side. Well, you've already plugged in 0 to the top formula. You just did it a second ago. You got 1. Cool. If we go back to the bottom and we plug in 0 to the bottom equation, we would have e to the negative 4 times 0. What's negative 4 times 0?
0.
And what's anything to the 0 power? 1. So does this limit exist? Why? Because I got, not just that it was defined, what did I get for both the left and the right side? I got the same number. Cool. When I get the same number, I can say, therefore, the limit as x approaches regular 0 of f of x is equal to 1. So it's defined. We didn't put D and E. We're good to go. The last requirement just states that we need the number from number 1 and the number from number 2 to be the same. Did we get the same number when we evaluated the function and when we found the limit? So what you write here is you say the limit as x approaches 0 for f of x is equal to f of 0. Okay, so now that we've concluded that the third requirement is met, what we're going to do, we just need to write our final statement, which is the final conclusion. Therefore, f of x is continuous at the point x equal to 0. So that's our final conclusion statement. So all of that is the full correct way you would want to write the justification for f of x being continuous at point 0. Questions?
Oh, is that the homework? The lesson?
Yep,
Oh, okay.
basically. So you're going to be writing these sorts of requirements for each problem. Can we do another one just so you can see another example? No, how about part B?
Or if you get a question done in my head.
Okay, for part B, let's start. We always start with the first requirement. The first requirement is that the function is defined. So if we were to actually look at 0, what does this graph read when x is 0? 0. We look for the closed-in dot. We found the closed-in dot at 0. It's at 0. Therefore, f of 0 is defined. And it's equal to 0. So that's the first requirement. It is met. F of 0 is defined. We go to the second requirement. And we need to find the limit. What happens to this graph as we approach 0 from the left side? What is it equal to? On the left side? 0. Okay. What about on the right side? What is it equal to as we approach 0 from the right side? Yeah, what's happening up here? What are we getting close to? 2. So does this limit exist? No. So that's a problem. We would say, therefore, the limit as x approaches 0, no plus or minus, does not exist. And already one of my requirements is broken, correct?
Yes.
When one of your requirements gets broken, you can just stop. You don't have to keep going because you already know it can't be continuous. If 1, 2, or 3 is not right, you stop and you say, therefore, f of x is not continuous at x equal to 0. That's about it. So the tough thing about this is you're going to really want to cut corners on how you write your justification, but this is the sort of justification we need. We need it to be formal, a formal justification in 3 parts. Does that make sense? Okay.